Now we go for question number 4. Okay, so we will learn about this, the theoretical of this one. So in chapter 2 and chapter 3. So however, this is actually the we some in UTM we have syllabus like this for our undergraduate. So for master student, we always says that it is some kind of Poisson flow or Couette flow. Okay, but it is okay. In undergraduate, we already give introduction about this one. So what I need you to understand here is actually I hope you could solve the simple integration problem like this one. Okay, let's say for this question, for oil flow in a pipe far downstream of the entrance, figure 1.10 and 1.11, the axial velocity profile is a function of r only and given by c over mu r square minus r square, where c is a constant and r is the pipe radius. Suppose the pipe 1 cm in diameter and U max is 30 meter per second. Compute the wall shear stress in Pascal if mu is equal 0.3 kilogram per meter second. So this figure is actually just to show how flow develop inside the pipe. So when water flow like this, so it start to create a boundary layer actually, and then at a certain length, okay, so the flow is well developed. Okay, normally in our calculation or our estimation, we are calculating behavior in the developed region, the developed flow region, because at the entrance here, okay, maybe it is quite chaos, and it is, it's always have their own unique behavior, because the entrance length is not so long. So normally we neglect what happened in the entrance length. Okay, so and then the other one is, I hope you could recall yourself about the idea of the idea of velocity profile like this one. Okay, because when water flow inside the pipe, there is an interaction between the solid surface and the molecule here. So will create the idea of no slip condition. So no slip condition means the molecule will not slip on the solid surface. So means the molecule will stick very hard on the solid surface. That's why you will find that there are algae around the pipe line. Okay, why algae could live happily on the surface of pipe? Because the velocity is equal to 0. So the no slip condition is actually reflect in mathematical expression as u equal to 0. So mean the velocity here is equal to 0, then it start to develop, and then it will reach the maximum velocity. So the maximum velocity here is at this condition. So it's depend on the situation. If your pipe is, the diameter of your pipe is very small, so maybe the maximum diameter will occur at one single point like this. So but however, if your pipe diameter is high, maybe it could create a straight line here to show that all of this is actually the maximum velocity. So this idea is actually not imaginary idea. It can be proved in experimental works. So if you see the example of the hydrogen bubble visualization, so you find that it can be shown that at the entrance here, okay, they are resistant on the pipe wall here, so make the velocity is not moving. The molecule is not moving. U is equal to 0, and then the shape is keep continuing like this, and then at one point the velocity, the maximum velocity, is at the center line of the pipe. So this is the behavior of flow in pipe. Okay, So the idea is from the question, we would like to calculate what is the, according to this question, so we need to calculate, okay, let's say the diameter is 1 centimeter and U is 30 meter per second, and then we need to calculate the wall shear stress if the mu means the dynamic viscosity of the fluid is 0.3 kilogram per meter second. Okay, the question is about the wall shear stress. So and then so okay, I just jump this one. Okay, this is the equation for wall shear stress. So the common equation is tau is equal mu du dy. Okay, so however in this situation we don't have the value of y. Okay, or you could imagine that we have Cartesian coordinate and we have polar coordinate. So in polar coordinate, so we change the value of y there as mu du and dr. Okay, so the simple idea of this one is we need to first calculate what is the value of du dr. Okay, what we could do is, okay, let's say we have an equation here, an equation that show the velocity profile, because this equation is u equals c over mu r square minus r square. So and then we have condition, which is the u maximum is occur at r equal to 0. As I said, for steady, for the developed region, the at small diameter, so the maximum velocity will occur at the center line of pipe. So we, okay, normally for circular shape, okay, we found that the center point is r equal to 0 and the maximum is r equal to capital R. So and then we substitute the value r equal to 0 and u is equal to max. So we have this one. Okay, after we substitute the value of r equal to 0, and then we know that the value of c here, as mentioned in the question, c is a constant. So when we have constant in our equation, we need to show the constant, show the value in terms of numbers. So how we could get that? So we could give the we substitute all the values. So we have c is equal to 30 times mu over r square, and then this capital R will show the maximum diameter, the maximum radius here. So if the diameter is 1 millimeter, so the radius is 0.005 meter. So we could get the constant is 3.6 times 10 to the power of 5. So and then we need to calculate what is the value of du dr, because this is the basic equation to calculate the shear stress for the round pipe. So and then we have equation of u equals c over mu r square, and then we could do the differential. We differentiate here, so we have du dr is equal to 2cr over mu. Okay, so and then we substitute here 2cr over mu, we cancel the value of mu, and then we could get 2cr, and then we could substitute the value, so we could get the wall shear stress is 3600 Pascal. So and then we could calculate the Reynolds number, so it will it found that the flow is actually laminar. Why we could say it is laminar? Because for flow in pipe, so we have 2000, and then we have start 4000 here. So Reynolds number less than 2000 is fully laminar. So it is good for you to use the word fully laminar flow. And then if the Reynolds number is greater than 4000, you could say it as a fully turbulent. Because if the Reynolds number is between 2000 and 4000, it is actually the transition between the laminar to the fully turbulent flow.